Hi guys, Miss Zimmer here with perimeter and area. This is our last chapter, our last sections that we're going to cover before the end of the quarter. Yay! And it is a familiar topic, but there are some twists and turns. We're going to be using a few things like Pythagorean theorem, 30, 60, 90, 45, 45, 90 triangles, and trigonometry eventually to solve some of our problems now. Now, perimeter, as we know, is the distance around a figure, whereas the area is covering the figure. So if we were going to paint something, or we were going to cover it in wrapping paper, or if we were talking about the coverage of how many tiles on a roof, or how many boards on the side of a house, what the coverage of those were, then we would be talking about area. Perimeter, of course, the distance around the figure. Now, in some of these pictures, you're going to get more numbers than you need, but I guarantee you'll most of the time get numbers that you do need. And if you don't have all the numbers that you need, we may be using something like trigonometry or special right triangles to find the missing pieces. Now, what's extremely important is that if you have a printer and you can print your formula sheets, that would be great. Otherwise, you may want to save those to your desktop so that you can easily access them anytime you need to use them. Now, area formulas such as square and rectangle are very familiar to you. We also used circle earlier in the textbook. Since then, we have moved on and we've been solving parallelograms a little bit, and triangles, of course. Triangles we've done before, but we may have not solved trapezoids, polygons, a rhombus, or a kite, and then some advanced circles. I'm actually going to ask you to add something called an annulus to here eventually, which is kind of like a tire. So, starting at the beginning, when you look at the formula sheet for a parallelogram, it'll tell you you need to use the base times the height. Well, where do you find a base and a height? Well, they're always at the right angle. This is if the height is inside the figure, it's always dashed. And if you look at this figure closely, if you took this off and you moved it over here, it would actually be a rectangle. So the base and height of a trapezoid is related to a rectangle. Now you can see in the picture here, we have numbers that, an extra one. So instead of saying 11 times 16 like we would in a rectangle, we're going to say 16 times 9. Our area is 16 times 9, and apologize, I did not bring my calculator with me. Yes, I did. Excuse me. It was just a little bit out of reach. Sorry about that. So 16 times 9 and 144. Now, if it's area, we need to have square units. So perimeter, we just use the regular units. Area, we have square units. And ultimately, we're also going to have volume. And volume is going to have cube units. But we'll get to the volume next week. Next one up. We have a triangle. And a triangle, we have 1/2 base times height. The picture shows the height inside the base down below. Now, it's certainly possible in a triangle that they have the height sideways with the base and the height. It is also possible if you have a right triangle, your base and height might be on the outside. So there are options to that, but always look for wherever the right angle is and where they connect, that's your base and your height. So our base and our height here, well, we have a height of 4. Let's write our formula down, 1/2 base times height. excuse me, that's an H. So 1/2, your base, actually we need to add those together, so your base is 10 and your height is 4. Now, if you notice here, this one shows what would happen if it goes all the way across, or if they only have one number over here, it might appear like right after that, underneath that perpendicular, so you can tell that it goes all the way across. And then of course this is 40, half of that is 20 meters squared for our final answer. Right. Now, a triangle kind of relates back to a parallelogram, because if you took this triangle and then you turned one upside down and put it next to it, you would get a parallelogram. So that's why we don't want this triangle, we only want half of our parallelogram, or one triangle. Pretty cool. Now, you could have, and you will have, some composite figures. You may have a composite figure like this one that's two rectangles, or a rectangle and a square, or a rectangle and a triangle, or a trapezoid and a rectangle. So it's important that you cut the figure into two figures, and I don't think any of the ones in part 1 goes any further than 2 figures. Yes, just 2. So we're going to cut this one. Let's cut it here. It's possible you could cut it this way as well. Now, if you cut it, it's obvious that this is 5 centimeters, just like that, because we have a rectangle there. But 19 goes all the way across. Keep in mind that this portion is 9. So I'm just going to move that 19 down. This portion is 9, just like at the top, 9 across. So 19 minus 9, this would be 10 meters. And I apologize for not drawing a very proportionate drawing in this one, but the pictures don't have to be to scale. They're not intentionally deceptive, but occasionally, especially when I freehand draw, they may look deceptive. Okay, so now we have first rectangle, this one. The area of a rectangle is length times width. So we have 13 times 9 for that first rectangle. And then we'll add to our second rectangle 5 by 10, which I know is 50. And the first one is 90 and 27, 117. And so we get 167 meters squared for that one. Or square meters. They might put like SQ and then M for meters. I was about to ask if there were any questions, but hopefully not. I'll see you at the Q&A on Zoom for that. All right, next one up, a trapezoid. So trapezoids, rhombi, kites. See here, I missed my board attached to the wall. A trapezoid, we know trapezoids have parallel lines, top and bottom. They also, in this case, has a height. So our height of 12 meters, and we have 13 meters up here and 17 meters here. And as I said, when it's sort of like in the middle of the line, that means it is the entire line, even if they don't have those arrows pointing to where the ends are. This is more common, that it's sort of in the middle of the line. So our formula for the area of a trapezoid, 1/2 the base, excuse me, 1/2 the height times the bases added together. So we take 13 and 17, our two bases. We're going to add those together and multiply it by half of our height, which is 12. So our height again is perpendicular, and our bases are the parallel lines. So now we have half of 12, which is 6. This is 30, and 6 times 30 is 180 meters squared. Right. Be careful. You only take half of maybe the height or half of your bases. Don't take half of both, because it's not distributed. Okay. You can multiply this. This doesn't need to be distributed because you have the two numbers. You can just add them together. right, the next question. Here's another composite figure. Let's see if this is supposed to be a square. Trying to do my best to get it as square-like as possible. I think I did okay. This is 30 feet over here, 30 feet, 17 feet, and 15 feet. Now, as you notice, the 15, they didn't tell you arrows up and down, so that 15 is going to stop right there. Even though they have this line dashed, that 15 is not in the center saying it goes all the way across. So what we need to do is we need to solve our triangle, 1/2 base times height, and then add it to our square. We can do length times width, or we can just say the side squared, Length and width or side squared, it works the same way. Okay, so our side squared is going to be 30 squared. We know our height, but notice this is a right angle, so this is not our base. We need to have this length. Well, it's a square, so that's our base again. So 1/2, 30 times the height of 15. Some of you out there are going to be very tempted to use that 17, but don't do it. Don't do it at all, okay? All right. Actually, I'm just looking at that, and it doesn't make sense for this to be 30. It can't be a square. They must have a mistake, because if that is a right triangle, then 17 squared minus 15 squared, I'm actually cranking out the Pythagorean theorem right now. This should be 8. So either they have a mistake. Let me do a quick calculation and see what they're doing here. Yes, okay. So I apologize. I said that this was a square. It's not a square. It is a rectangle. So let me tell you what I was just doing. This is not the side length. I drew it like a square. It looked like a square. And see, I got fooled by the fact that it is not to scale, that they actually made it look like a square, but it's not. And the reason why I know that this is not 30 is the fact that this is going to be a rectangle, length times width. But the reason why I know that that's not 30 is because this is a right triangle here. And in a right triangle, the hypotenuse, which is 17, has to be the longest side. So let's find our x value. X squared plus 15 squared is equal to 17 squared. So what I did in the calculator, I said 17 squared minus 15 squared, and I got 64 for x squared, and we know that that means that x is 8. Okay, so here's our first one where they didn't give us all the pieces that we needed, and I said we were going to use Pythagorean theorem, we were going to use special right triangles, we're going to use trigonometry. Here's our first one. So now that we have our 8 here, this is 8, this is 30. So the length and width is 30 by 8. That's the area of our rectangle. And then the base and the height are 8 and 15 there. So half of 8 times 15. That's going to give us 60 for our triangle, and then 240 for our rectangle, and then add that together and we get 300 feet squared. And that's supposed to say FT. Got a little bit smeared. All right, so that's our first composite figure and our first time where we had to find something that was missing. All right, the next two, we have a rhombus and a kite. A rhombus and a kite can be solved using their diagonals. A at least they can solve. You can solve for their area using their diagonals. All right, so let's start with our kite. Excuse me, let me get a little comfortable here. And all right, sort of a sideways looking kite here. Remember, in a kite, your diagonals are perpendicular to one another, and they're bisected. This is 2 and 2. This one's bisected, this one's not. This would be 1 and 3, and they're all meters. I'm just going to put an M here, but they all should have an M behind them. Now, the formula sheet tells us that if we have a kite or we have a rhombus, it's a rhombus on the formula sheet, but it can be a kite as well, that these are perpendicular, and this is considered diagonal 1, and this is considered diagonal 2. And if we use the formula 1/2 diagonal 1 times diagonal 2, we find the area. Well, the reason why that works is because we have two triangles here. The triangle at the top, which is 1/2 the height of 2 times the base of 4. And the same thing here. The triangle down here is 1/2 the height of 2 and the base of 4. So we actually have two triangles. And when you put them together, you actually get the formula for 1/2 of diagonal 1 times diagonal 2, which is the area formula I was mentioning from your formula sheet, which applies to a rhombus and a kite. So we would use 1/2. Diagonal 1 is all the way across 4. Diagonal 2 all the way across another 4. And it combines those two triangles together. So 1/2 of 16, 8 meters squared. We get to do the same thing with a rhombus. So let's say we have a rhombus. Always read what figure you're working with, because if you don't read and you assume that it's something else, you could be wrong. Now, a rhombus, they're doing this. They're putting little brackets, and it says this is 23 feet, and this is 29 feet. 23 feet, 29 feet. Well, notice that that doesn't give us all of the diagonal pieces. Well, it sort of does, because the diagonals are bisected. So this is 29 and this is 23. So when we do area equals 1/2 diagonal 1 times diagonal 2, if we just put 23 and 29 in, we're not going to have the right values. And you say, well, why would I add these two up? Wouldn't, if I put 23 plus 23 across is 46, and 29 plus 29, which is 58, aren't we going to take half of it anyway? Yes, but after we multiply them, so it's not going to be the same. So 1/2 of 46 times 58. 46 times 58, take half, and we get 1,334 feet. So if you kind of notice in a rhombus, one of these is a right triangle, and one of them has the base and height of 23 and 29. So we actually have 4 triangles, and they're all 1/2 the same base and height, 23 times 29. So what happens is this 4 actually works upon these and makes these equivalent. So you could do that as well. And it still gives you 1,334. So whether you do 4 single right triangles or you follow the formula, because you have that formula sheet in front of you, they both come up to the same answer. All right, moving on to the next part. I think I threw in a couple of rhombi, because Here's another one, and we get another problem with a missing piece. So this is a rhombus. May not be a perfect drawing of one, but bear with me. I'll go ahead and do this so that you won't have any doubt in your mind, because you know if the four sides are equal, that's the definition of a rhombus. And here are our diagonals. And they tell us the side length is 25 inches, and this is 7 inches. Solve it. Well, the problem is that even if we were going to use the right angle and do 4 triangles, if we took one of these triangles, we don't know the 2 side lengths here. So we can't solve it using 4 triangles. And if we tried to solve it using the diagonal, this one is 7 inches, yes, because it's bisected, but we don't have that diagonal again. So what do? We use the good old Pythagorean theorem. All the sides are 25. So in one of these triangles, if 7 is a leg and 25 is the hypotenuse, so let's go ahead and just call this x and x. We're going to solve for this x. It's the same here. X squared plus 7 squared is equal to 25 squared. Now you're going to have to trust me, that comes out to 24. You can go ahead and solve it. It is what we call a primitive. If you remember when we were doing special right triangles and Pythagorean theorem, they had some specific ones. 7, 24, 25 always comes out to a right triangle. So now x is 24. So this is 24. And that's not our answer because we're actually asked what's the area, and we know the area is diagonal 1 times diagonal 2, or 4 of this triangle. So 1/2 diagonal 1 all the way across is 14, and diagonal 2 all the way across is 24 plus 24, which is 48. And yes, it is sadly not to scale again. So the picture in my math lab is equally deceptive, so watch out for that. Okay, they're not going to look like what they are. So that gives us 336 inches squared. Okay. All right, there is another composite figure. I'm going to go ahead and skip over that one and let you handle it, and then I'm going to move on to another rhombus, but this time they give you less information. So back to another rhombus. We're still going to use the area as diagonal 1 times diagonal 2, but this time I think most of you will be able to figure out that if this is a 45-degree angle, then the rhombus is a square. Now let's pretend like you didn't remember that. If this is 8, this has to be 8 because in a rhombus, the diagonals bisect each other. Well, if it's a 45 here, let me move this 8 out of the way. Let me put it down here. If there's a 45 here and it's perpendicular, they didn't give you the perpendicular, you have to draw that in, and that means this is 45 as well. That means that this triangle, all 4 of the triangles are 45, 45, 90. What do we know about the legs? The legs are equal in a 45, 45, 90, so this is 8 as well, which goes back to the fact that if that's 45 and it's rhombus, remember all of these angles have to be the same, not just the alternate interior ones, but the ones next to one another, because the diagonals of a rhombus bisect the angles. And you're like, oh, we have to remember January? Yeah. Luckily, I tested you on that also right after Mardi Gras, right before we started all this distance learning. Okay. So what does this equate to? Well, diagonal 1 times diagonal 2, half of that for the area, 1/2. Well, this diagonal is 16, this diagonal is 16. So what is half of 16 squared, or 16 times 16? It comes up to 128. 128. And that is the unit that I should have written was centimeters squared. Next up, another composite figure, and then we are just about, oh, we got a couple figures before we wrap it up. I just turned the page and found a couple more. So this one is a triangle and most certainly a rectangle. Nice long and skinny rectangle. And you're like, oh, I see Miss Emma writing a 30-degree angle. I wonder if this has to do with 30, 60, 90 triangles. It does. Keep in mind our 30, 60, 90 formulas. I'll go ahead and draw it this way, so it'll be the same orientation. 30, 60, 90. This would be x, 2x, and x root 3. So notice, right triangle, 30-degree angle. 12 is the 2x value, so that means our x value, or this value, would be half as much, 6. So now all the way across would be 18 here. Now we still are looking for our height. We're going to need that height for our triangle, and we're going to need the width. That's the width also of our rectangle. So that would be 6 root 3. So now that we have those values, the area is equal to 1/2 base times height plus the length times width for the rectangle. Triangle, rectangle, composite figure, 2 formulas. So 1/2, our base and our height are 6 and 6 root 3. Remember, our base and our height always meet at our right angle. Plus our length times our width, 6 root 3, times our width of 12. So we're going to solve each of those. Now luckily it says round to the nearest tenth. So you don't have to have exact answers here. So yes, you may take half of 6 times root 3. And that comes up to 31.17. I know I said rounded to the 1/10, but we're not finished yet. And then, actually, this would be 1/8. So I'm going to round to the hundredths until I can finish the problem, and then I'll round to the tenths. Then we have 12 times 6 times root 3. So that was 124.71. And add them together, 31.18 plus 124.71 and 155.89 did not come up to the answer. Let me double check this. Okay, let me see what we've got here. Make sure that there are no other errors. 30, 60, 90. We did the half. It's actually a trapezoid. We can use the trapezoid formula, but I was using the composite figure, which should work exactly the same way. I found out exactly what I was doing wrong. Some of you probably looked up and you said, why is it that the x is across from the 60-degree angle? Because I put it in the wrong place. So my apologies. The x should be here and the x root 3 here. I apologize again, which means that this is 6 root 3 and this is 6. So the fact that I did not draw it to scale really messed me up a little bit. So the only thing that we need to do, we don't need to change our triangle because our two legs are still 6 and 6 root 3. The order doesn't matter, but it does change this because the width is 6. It is not 6 root 3, which makes this a nice pretty 6072, and now gives us the correct answer of 103.2. Rounded to the nearest tenth place and feet squared. So as I have demonstrated, you got to really watch out for these problems when they're not to scale. And your 30, 60, 90 formulas, remember your shortest side is x opposite the 30-degree angle. So this is our x value, this is our x root 3 value. And I just drew it a little bit wonky, so it even threw me off. All right, so luckily, reel it back a little bit and fix that up. All right, some of the terms that they're using are circles. You know radius, you know diameter. You know what a center of a circle is. You definitely, if we're talking about something inscribed, like this triangle is inscribed in a circle, that means its points hit the circle. The circle is circumscribed about the figure. So you may see words like inscribed and circumscribed come up again. It has been a little while. Another term that you'll see, because we have figures in a circle, so for example, let's say this is an equilateral triangle. You may have a center of a polygon. The center of this triangle is the center of the circle that would be circumscribed about it. And there's a term apothegm. An apothegm is not a radius like that. This one would be a radius. The apothegm would be from that center of the circumscribed circle, from that center of the polygon, perpendicular to the side, is called an apothegm. Okay, can't tell you where the term apothegm came from, but that is the word for it. And we're going to see some apothegms coming up today, just a little bit, and tomorrow a lot. Okay, so we're going to end with two figures that have apothegms. Actually, we're probably going to do a couple of polygons right at the end using some of these terms. So they're going to ask you for 3 angle measures in this triangle. Here is our center. If we were going to draw the circle back around, this would be the center of that circle, circumscribed about it. We're going to draw. They have them dashed in there. These are radii because if you can imagine the circle around it, they would go from the center to one of the points on the circle, which is the definition of a radii. And they're actually asking us for angle 1, angle 2, and angle 3. And they tell us that this is a regular polygon. Now recall, regular means if this is regular, the sides are equal and the angles are equal. Well, any triangle with equal angles, 180 split 3 ways is 60, 60, and 60. And all of these angles are split into 2 equal parts. So this 60-degree angle here would be split and 3 would be 30. Well, here's a 30, here's a 90, so this would be a 60-degree angle, 30, 60, 90, because they have to add up to 180. And then looking at angle 1 has to be a linear pair with angle 2, so that would be 120. Okay. Now, another option is to say if this is 30, this is 30, and this is 30, because all of the angles around here are those 60-degree angles split in half. 30 and 30 is 60 from 180 gives us 120. Okay, so that's another way to get right back to that angle. Okay, now let's deal with a pentagon. This is going to be a regular pentagon. So hexagon, I believe. A regular polygon, it is a hexagon. So 1, 2, 3, 4, 5, 6. Not bad. Oh, no, that's kind of bad. It's lopsided, excuse me. Do a little figuring right there. And still a little bit lopsided, but not too bad. All the sides and all the angles are equal. Keep in mind that if we have a hexagon, think back, 180 times n minus 2 divided by n told us what one of these angles is going to be. Well, if you put in 6, 180 times 4, and 6 minus 2, and then divided 6 ways is going to give you 120 for one angle. So keep that in mind for this problem. It's going to be important. And even if you forget this, there's another way to do it. So if you forget this formula, we're like, oh, thank goodness, there's a second way. All of these are really dashed lines, but I'm just going to draw them solid because that's a lot of dashing. And one of these triangles, just one, is equilateral in a hexagon. Now, I can prove that to you pretty quickly. You look around the middle, I just drew a circle. A circle is 360 degrees. So these 1, 2, 3, 4, 5, 6 angles have to add up to 360. Well, these are equal angles. They're all the same distance apart. So 360 divided by 6, each one would be 60 degrees. So I could go around to each one. They would all be 60. And all of these are radii of a circle going around it, so they would be equal. So this 60-degree angle, 120 left, 60 and 60 split equally between those two base angles of an isosceles triangle. So the easy thing to remember is that if you're given a hexagon, that all of these triangles are equilateral triangles, every single one. 1, 2, 3, 4, 5, 6, because it's a hexagon. So they're going to ask us a few questions here. The problem, going back to that for a moment, that was just a quick lesson on hexagons. Now, if I were to draw a pentagon or an octagon, they are not made of equilateral triangles. That is totally unique to a hexagon. All right, now that I've almost got this sort of back in shape, they have an apothem, and they want to know what is the degree measure of 8, what is the degree measure of 9, and the degree measure of 7. Well, we just said the measure of angle 7 is 60 degrees because it's an equilateral triangle. 60, 60, 60. 8 is just half of that angle, so the measure of angle 8 is 30. And the measure of angle 9 is one of the space angles down here, so that would be 60. So just keep in mind that if we go to each one of these apothems, that each of these triangles now has been split. So instead of 6 triangles, we have 12, and every single one of those 12 triangles is a 30, 60, 90 triangle. Because an equilateral triangle split right down the middle is a 30, 60, 90. Okay, our final questions. So find the perimeter and the area of a regular polygon given an apothem and a side length S. So you will need to know the names of your figures. This first one is called a non-agon. So if you look on your formula sheet, it tells you the area of any polygon is 1/2 AP. A being the A being the apothem, and P being the perimeter. This particular figure, they tell you that A is 22, so the apothem is 22. We have that half. That's part of our formula. Just go ahead and put parentheses around that. So all we need is our perimeter and we're good. Well, they tell us that S, our side length, is 16 inches and that it is a nonagon. A nonagon has how many sides? 9. So 9 sides. So what this means is that your perimeter, or the distance around, is the side length times the number of sides. So 9 times 16. We often call that S times N, side length times number of sides. Now we're just ready to calculate and get that one completed. And that will give us our area. Well, and by the way, our perimeter, I already said, was 9 times 16. That's one of our questions, which is 144 inches. And that is not squared, that's just inches. And then you can use that 144 here, our perimeter, and 1,584 inches squared. Because now we're dealing with area. Area squared, perimeter not squared. And those questions, the last couple from our area part 1, will ask us for perimeter and area there. Great. I hope this was helpful. I literally worked through almost all of those problems, not the vocabulary, and I think I might have skipped maybe 1 or 2 problems that were the same. I will catch you for area part 2 next. Bye. Have a good day.